Okay, awesome. So yeah, Professor Nubik is in Hawaii. So we'll talk about structured prediction today, no quiz. I hope you all had the chance to return your assignment too yesterday. If you have not received an email yet, don't worry about it. If you sent it, you're good. We'll get to it. Okay, so let's get down to it. So we will talk about, okay, before we start talking about structured prediction, can someone tell me what the difference between a generative model and a discriminative model is? So if we have observed variables x and latent variables y that we somehow want them to connect them, what is the difference between a generative model and a discriminative model? No one? Someone? Yes?
In a discriminative model, you model conditionally, but in a generative model, you model jointly. The probabilities change.
Okay, so basically, yes. What this means is that a generative model describes basically a story of how the variables that we see, the observed variables, the x, how they were generated, how they came to be. And the story is somewhat like there's a distribution over the latent variables, and they generated the latent variables y, and they generated x. Okay. The discriminative model instead exactly just models the probabilities of y given x. Period. Okay. And in some cases that's better. Some cases it's not. So in some cases it's tractable, and we can actually model it without having to deal with modeling the p of y that the generative model has to do. And that's what we're going to talk about. So a classic example of structured prediction is sequence labeling. And what does that mean? Basically, it means that for every token that we have in the sentence, we want to output a single tag. And that could be either like a part of speech, like I is a personal pronoun, hate is a verb, this is a determiner, etc. Or we might have something even more sparse, where like named entity recognition, where basically for every token we have a tag telling us if it is an entity or not. So all these 0 are not named entities. And then Keanu Reeves is a person, so we have a tag that's like begin person, like intermediate, like middle person, or end person if someone has 3 names, etc. So one way to do this is just to treat that problem as an independent classification problem. Maybe we can take in some context. So for every sentence, for every word in the sentence, we have, okay, padding in the beginning and the end. We get an embedding for all these. And now we can, in order to provide a label for the first word, I, we can just train a classifier that will receive, for example, a fixed context and produce an output. And we can do that across the whole sentence. So what are possible problems that can arise out of that? No? Any problems with this? These were great, right? Problem is, this independence assumption is actually very strong. To the point that if you ignore context, then you have no guarantee of like a valid or consistent structures. To go back, nothing stopped that previous model here from producing a sequence of tags that would be completely unheard of. Like nothing would stop the model here from outputting verb, 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 right? And yes, you could do that, but clearly this is wrong. So what if we use history and we model our input using a recurrent network like we have seen? So what if instead of using a fixed context classifier, we put all of our embeddings through an LSTM, forward and backward or whatever, and then we use that to receive an intermediate representation for every word that we put through a classifier. That should do better, and it does, but it still suffers from some issues. The first of all is that, okay, now we don't really have any independence assumptions because basically the two recurrent networks are supposed to capture all of the context of the sentence. But it's really hard to calculate the exact probability of the whole sequence of the outputs. And we need to do approximate search. So we've talked already about beam search, or the way that we can generate the outputs from an RNN, right? We can sample, we can just get the argmax with greedy search, or we can do beam search, which solves a lot of the problems, but beam search is still not exact. So what we need to do an approximate type of search. And a recurrent model suffers from these types of issues: exposure bias and label bias. So what is exposure bias? Exposure bias is basically arises from the problem that we train the model in one way, but we test it in a different setting. And here's exactly what this, where do they have it? Oh, so basically, when we train, like the standard way of training an RNN is by using teacher forcing. What this means is that in every step, right, although we predicted an output, we know what the correct output should have been, and that is what we feed back into the decoder, right? So during training, the decoder always just receives the correct input. However, during testing at inference time, we don't do that because we do not know what the correct input is. At inference time, for every decoder step, we take the argmax, or if we're doing beam search, either of these. Like let's say we're doing a beam search of 4, you'll take each of those top 4 and you will feed them back in. So there's no guarantee that these are actually correct. So there's this mismatch between the setting in the training and the setting in inference. So here's like visualization, right? We trained on correct settings. So at any given time step, the input to the decoder was the correct tag. However, what if during inference, instead of the correct tag, we output a wrong tag? Then that's what we will feed back in, and this could create a cascade of errors. Or not. Ideally, if the model is robust, then it should be able to recover. But this is a general problem which is called exposure bias. Another thing is label bias. So you're all familiar with more traditional FSTs and automata, right? So label bias is the notion that if you have transitions that have basically very, very low entropy, which means that are very likely to go to the next state with high probability, then these states might just completely ignore their observations. So the idea is to transfer that into the neural network realm if we're doing name entity recognition. And throughout our training, we have always seen an end of person tag following a begin of person tag, right? Because we have only seen named entities of persons that are of length 2, okay? If we have only seen that, then then at inference time, we will only basically prefer after a begin of person, we will almost always prefer an end of person, right? Even if at inference time we have a person with a name that has a length 3, we have never seen this in training, so we're biased much more towards the labels that we have, only towards the labels that we have seen during training. Okay, so basically all of these models with local dependencies have issues. Either if we assume complete independence, then we have the problem of not coherent output potentially. If we have a history-based model, again with an RNN, again we will have these problems of exposure and label bias. So what we want is a model that does make some independent assumptions, but it doesn't. It's not entirely independent. So we want something like local dependencies. And the way that we want to do exact inference on it, as well as training. And the way that we do that is basically with conditional random fields, or CRFs. So let's see how these things work. So as a reminder, what we want is to learn the correct distribution of y given x of sequence outputs y given some sequence input x, or well, in the case of language, it's usually sequences, right? Or it could be whatever. So ideally, we would want to model every candidate output given that x. So the probability of every y of every output would be basically the probability that our model assigns divided by the probabilities of all the, if we enumerate all of the possible outputs, yeah, that would be the denominator, right? So in the globally normalized model, the probability of a y given x will be just this c of y and x divided by the sum over all possible candidate size. Sorry, in Greek, psi is just c, so it's really weird for me to just say psi. So just bear with me. So yeah, so we'll refer to these c functions as potential functions. So conditional random fields make an independence assumption that's like between global and completely independent. So a globally normalized model would have the observed inputs x. We have all the outputs y, where they're all dependent on each other, right? And hence, that's why it's globally normalized model. Now, this is hard to implement or train or approximate. So, so again, in this case, that's the general form. So the probability of every y given x would have that form. We have the potential function over a given sequence. If we could enumerate all of the sequences, then we could calculate the denominator and we could get our scores. However, this is too complicated. So we came up with first order linear CRFs. So basically the assumption here is that each of the outputs is dependent on the neighboring ones, on its neighboring ones. So notice that here there are no arrows, so it's not directed. Okay, so it's not like y3 is dependent on y2 and x. It's y3 is dependent on y2, y4, and x. Okay, so now the potential functions can be summarized as follows. So for every y, we will have its own potential function, c. And the probability of the whole sequence will just be the multiplication of all those. And then again, the denominator is a summation over all of the candidate sequences. Okay? So, what are these potential functions? So I put that thing over there so it's easy to follow on top. So we have the c for position I, given the previous c, the previous y, the previous observation, the current observation, and all of the inputs x. So we have the transition probability, which is this capital T, which corresponds to the horizontal connection up top. Okay, and then we have the emission probability, which is the probability that x was emitted from y. If you're thinking of we didn't talk about before, but there's a connection between HMMs and CRFs. HMMs are the generative version, and CRFs are the discriminative version of an HMM. Okay, and HMMs traditionally we have exactly those two things. We have transitions from state to state, and we have emission probabilities from every state that output the observed variables. Okay. Yeah, so the equivalent again here is that we have those transitions and we have those emissions. probability, and we have some bias, which we won't talk about now. So if we wanted to model that with a neural net, basically we can substitute this transition and this emission functions T and S that depend on X, right, the input. We can just substitute it with F, which is whatever neural network you desire. So basically, again, we have a weight matrix for the transitions, right? W for the transitions, times the F, the function that gives us, that is conditioned on the input. And then we have the emission probabilities, again, that is some F conditioned on the input. So these Fs are the ones that we will learn using the neural net. Okay? There's a much simpler version, which is even easier to grasp. What if we have the transition probabilities be just a weight matrix that we can learn, and the neural net takes care of this F that only has to do with the emission probabilities. Okay? This reduces the number of parameters, and I think that in practice will do as well, maybe, I think. So the way that this looks is basically like that. We, again, have, for an input sequence, we have our embeddings, our BILSTM or convolutional networks or whatever you want. And now, for every position, we use that to learn, to basically learn the emission probabilities for every CRF state, or to bias the emission probabilities for every CRF state to be accurate. So yes, is that distinction clear? Like, we're not directly using the neural net to output whatever the tag is. We're using the neural net to basically bias or to learn the emission probabilities for every position. Okay. So how do we train and decode with CRFs? Who has seen the forward-backward algorithm before? Awesome. And I guess it's the same for the Viterbi algorithm, right? So this will be easy to follow. So again, this is the same as before. With the probability of a given output sequence, so an output sequence given an input X is basically this fraction. And the top thing is easy to compute, right? We already said that this PI is like a function of the emission, the transition probability plus the transition matrix, which is again probability, plus the emission plus this bias. The problem is this denominator, this z of x, which basically sums over all possible sequences, all possible outputs. So during training, the hard part is exactly computing that z of x, this summation over all these outputs. So if you were to write it down, that's what it would look like. And now the decoding problem would be finding the one path through the CRF that has the maximum probability. Okay? So the problem, and why especially this z of x is hard, is that you have to go through all of the output space, and as the length of the outputs grows, then the total space grows exponentially. So yeah. So that's why this has found like application in the case where the size of the output vocabulary is small, like part of speech tagging, named entity tagging, dependency parsing or dependency tagging. Whereas, although there is some work on using this for machine translation, this hasn't really caught up yet. Because, why? Because the final CRF that we put on top, right? What is its size? It's the size of the vocabulary times the length of the output, right? So if the size of the vocabulary is like 13 universal part of speech tags, that's awesome. If the size of the vocabulary is like 120,000 English words, then this will just take too long to train, to do anything. I mean, it's doable, don't get me wrong, but okay. So what we need to do in order to compute this z of x is note that the assumption that we made about the dependence between the y's really help us. So basically, each output y, right, depends on the input and depends on its nearby labels. But given two labels, y3 and y4, all the others do not matter. So basically now, instead of thinking of the nodes in the graph, think of the edge that connects the node, the two nodes. So basically, if we know the scores of every sequence up to this output at position n minus 1, let's say the output at position 4, then we can easily compute the score of every sequence up to position 5. Why? Because we have all these transitions in between that are only dependent among them. Basically, if we have everything on 4 and we want to compute 5, then we don't need to use anything else before or after. Yes. So basically, the way to think of this is that you can think of it basically, this is Graham's work, as a pre-calculation that happens at every previous step before we think about yn. So you can see how this evolves into a neat dynamic programming algorithm. So let's see how this would work. So we start with an initial state which has one output, right? Like that we don't really need to learn. And now we have to calculate all the transitions and the emissions for position 1. So at position 1, we go through all of our vocabulary, and now the score for the sentence up to position 1 will be for each of those labels will be the following. We'll have the transition probability coming from start of sentence going to noun and n, plus the emission probability. The emission probability is the probability that natural is emitted from the tag noun. For the second case, we'll have start of sentence going to JJ, and then JJ emitting natural, and so forth. Now that's fairly easy, right? Because we only have one possible state that we can come from. Okay? So what happens in the middle part? In the middle parts, we have vocabulary size, like tag size, tag vocabulary size, possible paths that could lead into the current state that we care about. So basically, the score for every tag in the second position would be the sum over all of the previous tags that we can use to get into it, right? So the score for position 2, the tag at position 2 being noun, it will be the sum that we started from the first position noun going there, that's the transition probability. It is the score that we were, the probability that we were in the state 1 and n, plus the transition probability, plus the emission of language from noun. Okay? So that's the first path. Second path, that we started from the second, the 1JJ, so that's the score, the probability that we started there, that we were there, plus the transition probability to go to 2 and n, plus again the emission, right? So basically what we do is for every state, we enumerate all the paths that lead to it, okay? And the proper thing to do is to operate on log space, because you don't want to have like underflow problems. Because otherwise all these would be multiplications, okay? Yeah, so we did that for 2 and n, and now we need to do that for every state in position 2, and then basically that's what you do for every middle position, right? So the number of things that you need to compute is if you have n tags, then for each of those n tags, you will have n previous paths to compute the probabilities of, but it's doable. So, and then after we finish and then we have exhausted our sequence, we need to emit the end of sentence symbol, which will basically sum up the whole computation. It's the equivalent of like the final state in an FSA, right? So again, now the score of the last token having been generated from an end of sentence will be again the log sum x over all the paths that we could take to reach the final state. Okay? Yes.
So I'm having some trouble understanding how is this different from HMM?
This part is not the way that we like. What do you mean that it's not different from an HMM? So it's just.
This looks exactly like an HMM function.
Yes. The difference here is the way that we compute the probabilities, the emission probabilities, or the way that we compute if you had the first version that we talk about the way that you compute the transition probabilities. So basically, well, there are other differences. So the HMM assume when you train an HMM, right? You start from the y's and you generate the x's. So when you're training an HMM with EM, right, you need to learn both the probability of the y's and the probabilities of x given y, right? Here we just have the probability of y given x, which is what we model. But yeah, you're right. This is written with like the x is being generated. So I think, yeah, good point. But is that clear? Okay, so now we have this whole CRF graph, and we have computed all of these probabilities. So how will we compute that denominator, right? So we define a partition function P, which P sub T will mean the partition, the function up to length T. Y will be the label that we end up. So if you think about I'll do it here. So P sub T, so P sub 2 for VB given X would be basically the sum of all this will be exactly what we computed. It will be the sum of all the paths that are of length T and end up by emitting label Y. Okay? And now if you expand exactly what this means, so you will see that you can do this trick where you can take the last CT, basically, take it out, and then what's left inside is essentially the partition function up to the previous length, right? So the overall denominator will be the sum of all the paths that have length L, if L is the length of the sequence that we want to have, that end with some label. Now, in the part of speech tagging, or basically in any problem, because we pad the sequence with start of sequence and end of sequence, we pad the input. We also have the output tags to be start of sequence and end of sequence. So this summation is not really needed. So basically, what you would have is that the z of x will be the partition function, the P sub L. So you have gone through all of the sequence of the end of sentence given x. Okay. Right. So so this is how we populate. Sorry. So now we calculated this z of x, right, which was the denominator that we needed. So note, how do we decode when we went forward through the CRF, right, we had the summation for every state. So we summed all the probabilities of the paths that came into each state. Now, if instead of a summation, we do a max, that is determinative, okay? And that will allow us to decode and find if we go through again with the partition function, etc., to find the highest probability sequence over the output space. I mean, you already said that you have seen forward, backward, and Viterbi, so you can understand how the dynamic programming would go. So one question is, how do we calculate gradients here? So the intuition is actually very simple. If you think about the CRF, right, we have computed all the probabilities of all the possible paths, right? Because we have at every step, we have all the candidate tag outputs, okay? So we have all the possible paths, but only one of them is correct. So what we want to do is go through that path and maximize its probability, right? So our loss will be the difference from like a probability one path that is the correct, from minus the actual probability that we gave, that our model gave to this path, right? There's a discussion about this at the required reading, but the good thing about this thing is, well, okay, let me go back. If we want to, it's still good, don't worry. So if we want to, so we have the path, and it's constructed by different edges, right? So what we need is we want to propagate gradients through each of those edges, right? So the way that we do that is we need for every gradient the marginal distribution. So how do we get that? And here's what the previous computations with the forward-backward come in hand. The marginal distribution for a given edge across the whole CRF is given by basically using the forward-backward. So we sum with the forward algorithm all the paths that lead to one side of the edge, okay? We have with the backward algorithm all the probability mass that left this edge, right? So again, the forward path for every state will give us these alphas there will give us all of the probability mass that ended up in that state. Okay, the backward path will tell us as we go back all of the probability mass that started from that state. Right? So basically, what we want is all the probability that flows through this transition. Right? So the probability that flows through this transition is the probability that came in times the potential of that transition times the probability that came out. I don't know if it's the correct way to think about this through probabilities, but I like to think of it as like a flow of probability mass across the whole CRF, right? You start with the probability of 1 because the probability of a start of sentence is 1, and then you have all the candidate paths that eventually converge into an end of sentence, right? And what you want to do is maximize the probability of the correct path. So so the marginal distribution will be that divided by the probability over all of the possible paths. The good thing is that you don't need to really implement anything in terms of like computing the gradients here, etc. So if you're using like a network, a PyTorch or TensorFlow or Dynet or whatever, they will have autograd. So if you define if you do the forward, if you do the backward, and you define the probabilities, the marginal distribution for each transition from -1 to yi minus 1 to yi, that we have already seen how to do that with the forward and backward, then you can just say, okay, now my loss is 1 minus that probability. Because we would have wanted this probability to be 1, right? Like the best, like the highest probability that a path can have is 1. Like if we always chose the correct path with probability 1, that's the best we could do. So yeah, is that somewhat clear? Very clear, or just somewhat clear? Okay, lots of nodding. That's good. So let's see how this can be applied for sequence labeling. Going through this work by people here at CMU. So our goal is to be a completely end-to-end neural model that will do sequence labeling, and that it will not do any feature engineering or data preprocessing. This means basically in the past, people would have something like collect features like n-grams, bigrams, subword, like character probabilities, etc., that they would use in order to do, say, part of speech tagging. So instead, what mine others did, they converted it into a fully neural net that has a CRF layer on top. So they use 2 levels of representations for each source word. One is at the character level, one is at the word level. So the way that these things look is at the character level, you split the token into characters. You might pad it, and then you can do a bunch of convolutions among them and match pooling, and that basically gives you a representation that is informed at the character level. This is what people are still doing actually. For example, if you're doing, if you want to do modeling with not uncs, and you can have a bunch of word embeddings for a fixed vocabulary of 100,000 words, but then in order to deal with everything else, you can have a character representation give you an embedding again for these uncs for which you do not have a proper embedding. Or how many of you used fast text in the first assignment? Right. So fast text does basically a very similar idea, right? It learns small embeddings for character n-grams and combines them for every word in order to produce a final representation for every token. Okay. So here's that's how they get the character level representation of every token. We also can have a word embedding, and I think in that work they use just globe vectors, and now they concatenated the two, and that was the final representation of each input token. Now, in order to capture history and like the dependence across the input, they put it through a forward and a backward LSTM, and they used the outputs of the LSTM at every position to basically learn the emission probabilities for every state of the CRF layer. Yes. Training details. Okay, you can go through it. Something that was pretty cool was that they took good care of properly initializing the parameters. So it's generally a good idea, especially if you're dealing with lowish resource scenarios, to keep the parameter space constrained. So for example, the character embeddings, all the parameters for those embeddings are sampled from a very, very small, basically, sphere. And they use pretty high dropout. That's become basically standard now. Okay, so the way you can see that across their experiments that a standard bidirectional RNN for pattern speech tagging already achieved like a 96.7, right? So yes, it is able to capture like history, and basically it is able to overcome exposure or labor bias to some extent, but we were able to get such accuracies with older models too. So you can see that substituting a standard RNN with LSTM does slightly better. Adding the subword information, the character level information with the CNN further increases the performance. But you can see that the final jump to something even better is achieved using the final CRF module, because now we can have exact inference over all of the sequence. Okay, and basically, if you think about it, what the CRF models do is essentially generate the whole sequence at once, right? Because they look over all the possible outputs and they pick the best one, right? Instead of having an RNN going and generating one by one, where the decision that you made for the first, the second, and the third is not really informed by the decision that you are making for the 16th or the 17th time, okay? And yeah, so even better results in named entity recognition, where they were able to increase the state of the art from like 85 to 91. Yeah?
I'm confused about the output of the BILSTMs. Like, are there emission matches of the CRF or the transition matches?
Are they what?
Like, what's the function of the BILSTM's output? Are they used as the CRF's emission matches or transition matches? Like,
Oh, I'm pretty sure that it was just for the emissions. So basically, the emission probability is just a number between 0 and 1, okay? So the way that you can think about it is that we are given a feature for every position, a vector of features, which we have either learned by hand engineering features, or we have been given a set of features from the LSTM. Okay? Now we take that vector, and we can have a vector, let's say V, from that position, right? And then you can just put it between a, like, okay, plus V or whatever, right? You can just put it through a sigmoid and get a 0 and 1 score. And you can do that for every state, and learn this, and go further down, like, and you're learning that too, right? So this is the emission part. Make sense? Yeah. Okay, so another cool idea that actually combines reinforcement learning. So here's an issue with, again, all this. And we talked about reinforcement learning. And that is, we are training with maximum likelihood. We generally have like a loss that is at the word level. With the CRF, we're maximizing the whole path, the whole sequence. But basically the idea is, how can we use a different type of reward, like a score, like accuracy or blue score, in these type of globally normalized models? Because again, so far with the CRFs, we still have the distinction between what we're optimizing and what we're evaluating, right? So again, when we have structured prediction like part-of-speech tagging or named entity recognition, we can have different reward functions for each of those problems. So for part-of-speech tagging, we would have something like token level accuracy, or for named entity recognition, we have F-score. For dependency parsing, we might be computing like label attachment score based on the tags that we output. Or for machine translation, we could have like basically a blue score, a meteor score, or a TER, or any of all these other metrics that have been proposed and are probably better than blue. So the question is, do different reward functions impact our decisions? So let's think of, so basically the problem is that it's kind of hard to answer that question. So let's, in this example, let's say we have a bunch of inputs and outputs drawn from the same distribution, okay? That's data 1. And we have another set, data 2, that are also drawn from the same distribution, right? This is the training or testing set for data 1. This is for the second case. And now we have the first task, and we learn a model, H1, that learns to predict some outputs given some inputs, right? So basically, we're training on these X and Y pairs. So we do that for both of those cases, and we get my model H1 and the model H2, right? So what is our reward on the first case? If we have a function R1 that gives us the reward, we get a number. In the second case, we have a different reward because whatever, one of them is blue, one of them is meteor. Okay? We have a different reward, and we get the reward in the first case, and we get the reward on the second case. Does that tell us anything about models 1 and 2? And the answer is, it depends. So let's see an even example, a different example. The box is a reward function. Each box is a reward function, okay? And it's a very simple reward function. If we get it right, we get $1 million. If we get it wrong, we get nothing, all right? And we have the first predictor that gets it right 80% of the time, okay? The second reward function is the same. It gives us 1 million if we get it right, 0 if we get it wrong. And we have another function, h2, right, the predictor here, that gets it correct 20% of the time, right? So we are given with the option of choosing between the two functions. So if the reward is the amount of money that we get, we will make our decision based on the expected reward, right? So what is the expected reward on the left side? Huh? I'm deaf. 0.8 million. Yeah, 0.8 million. The expected reward on the right side is 0.2 million, so we will clearly decide with the one on the left. But what if the situation was slightly different, right? So yeah, money. Okay, so what if it was slightly different? What if the second reward function gave us $1 billion if we got it correct? Now, the expected reward on the left is the same, but the expected reward on the right, now it's $200 million, right? Which is much higher, so we would decide to go with that. The takeaway is that if the reward functions are not the same, then we cannot really make inferences about the two predictors, okay? Or like correctly informed inferences about the two predictors. So there are a bunch of previous methods that consider reward, and you saw a bunch of, one of them, I think, in the reinforcement learning class, right, a week ago. And what all of them do, okay, not all of them, but you saw, we talked about reinforce. The last method there basically combines maximum likelihood with rewards. But we're not going to talk about those. We're going to talk about minimum risk. And the idea is very simple. Think of we have the reward, which is like the good points that we get for getting the output correctly. The risk is basically the error. It's the opposite. It's the error, is the penalty that we would get for getting the output wrong. And sorry, that's the penalty, the error. And the risk is basically the probability that we will get the output wrong. So what we want to do is to kind of like reverse the problem. Instead of maximizing the correct output, we want to minimize all the probabilities of all the wrong ones. Does that make sense? Kinda, yes. So yeah. So basically, this loss function, this minimum risk loss function, will be the loss that we get from all the outputs if we get them wrong, right? So basically, this error function could be something like 1 minus blue if we're doing machine translation, right? Or 1 minus your accuracy if you're doing part-of-speech tags. So basically, the error of the correct output is 0, so we get no loss from there, right? For every other sequence, we will have some error, so we have some non-zero loss. And we multiply that by the probability that our model assigned to each of those outputs y. So if you use this as a loss function, that's awesome. It's kind of like hard. Again, the problem is enumerating all of the possible outputs. And this was presented in the setting of machine translation, right? Where like actually enumerating all the possible outputs is impossible. So what Shen and I proposed is instead to sample a bunch of outputs, make sure that you include in your sample the correct output. Okay, so for every input X, you sample from your output, from your model 10 outputs, and now what you want to do is minimize the risk over the wrong ones. The way now the difference between that and before is that we have this re-normalization term where in order to make this thing sum nicely to 1, now the probability is computed within the sample. Right? So if we sampled 2 things and our model assigned, let's say we sampled 3 things. One is the correct output. One is the wrong output that our model gave 0.2, and one is another wrong output that our model gave 0.2 again. Oh, and our model gave 0.1 to the correct one, right? Now we'll just re-normalize that so that 0.1 becomes 0.2, 0.2 becomes 0.4, just over the sum. Did I explain that correctly? You get it. Okay, so basically you just do a renormalization over the probabilities that your model assigned to your samples. And you just minimize that, right? You want to minimize the probability that your model will assign to the wrong answer. And indirectly, you're actually maximizing the probability that the model is assigning to the correct one. Or actually, what we will have done is combine the two. So you can still have your maximum likelihood loss, and you can also eventually, after your model has learned, start using the minimum risk training so that you will also keep the probabilities of the incorrect outputs down. Yeah, and on a final note, if you can have an error function that can be decomposed into all of into each token that you have in the output, then you could basically calculate risk for each word. So basically, this is just an illustration of how you could have minimum risk training with CRFs, where now you get basically you have an error function that gives you the risk over each of the wrong ones. PRB, like the personal pronoun, is the correct one for this task. And you can, at the same time, well, if you think of the whole CRF, right, the standard training would be just maximizing the correct path. Now what you can do is maximize the correct path, but also minimize the probabilities of all the other wrong paths. Yeah, that's all for today, actually. That went fast. Sorry about that. I hope, if it's not clear, I'll stay here for a while. If not, you can always ask. The reading basically covers also everything you need. But if you were to implement this, I just want to point out, if you were to implement this, really all you need to do is define your transition matrix, right? The W's that we saw before. You can do the forward, do the backward, using the exact same equations that we explained here. And now the marginal distribution will be just this fraction that we saw, the alpha times the C times beta, the backward probability, divided by the global denominator, which is the partition function at the final, at the length at the final state. And that's all you need to do. And then you just maximize those probabilities and or minimize the probabilities of all the other paths. Yeah. Yes. Here? Oh, here. Yeah, so the correct answer is personal pronoun. Okay? And our model assigned all these probabilities to, our model assigned these probabilities to all these outputs. Okay? Well, yes. So this is the error that we get from each of those outputs. So the correct one has an error of 0. For some reason, noun is less wrong than determiner. This could just be 1, 1, 0, 1. It's fine, right? So yeah, and then by multiplying that, then and if you minimize that, then you're minimizing the risk of outputting the wrong task. Yeah, that's it. Unless there are more questions, I guess we're done early. Next, on Thursday, Chunting and Junshan, we're going to talk about latent variable models. It's pretty cool.